hopefully we're rolling. So Omar, this is for you. Stirling's formula derivation. It's a lot weirder than you might think. I love these kind of problems because it's like, I feel like one of the quirky hearts of number theory is like these random approximations. Oh, they're like meaty, important approximations, right? Because the first one that comes to mind is prime number theorem, like approximating the number of primes, like pi of n, like less than some n. But here we have Stirling's formula. This was, if I sound a bit, it's very arbitrary, or put it that way. It's very arbitrary. I'm just gonna check if this is in frame real quick. Okay, we're good. Okay, dramatic angle change. We love that. Anyways, so yeah, the theorem statement. I'm gonna put it up here. Very organized. It's that n factorial is approximately. Let me just check my notes here. Hold up. The theorem statement is low-key the hardest part of this. Like, not the hardest part, the most annoying part to remember. It's like, hold up. Where were we? Oh, yes. Square root of 2 pi n to the n plus 1/2 times e to the negative n. Now, I think the part that is like most like well known, I feel, is like the n to the n part. Because like if you take the log of this, then like it's well known that like log of n factorial is like approximately like n log n, like digits about, on the order of this, in the order of n log n digits. So that's like well established stuff. E to the negative n quickly becomes irrelevant just because it's an e to the negative n. And this is just a constant. And as we will come to see, this constant is very important. So yeah, that's where we are with things right now. And so where do we go from here? So clearly we have some starting steps. We have log n factorial already. So let's consider log of n factorial. So consider log of n factorial. So this is log of the product 1 through n, obviously, just by definition of factorial. And log products turn log sums. So we have log 1 plus log 2 plus log n. Now, here is where we introduce just like back to the calculus days. I'm going to say, let's just say I have the graph of log of n here. So we have our good old intersection at 1, and tapering down onto negative infinity, 0. Everyone, we all know log. I think we can agree log is increasing. So I'm going to set some value n here, and then we consider n minus 1 and n plus 1. So what I'm doing here is, so if I consider n minus 1 and n plus 1, so as you can see, we have a gap of length 1 here, and we have a gap of length 1 also here. So if I drew, so this is log of n. So this point is n log n comma log n. And so if I drew like this here, so yeah, hold on, let me just. The idea is like we're just gonna like take integrals and compare them to log of n. So as you can see here, so if I take n minus 1 to n of log t dt, that's going to be less than log n, just because like the max is log n and it's spanning length 1. So just by like this top rectangle would be log n, and then this top rectangle up here would be log n plus 1. So by the same logic, we have n, because this now serves as a lower bound for this integral from here to here. So it's just like integral shit. So log of t dt from n to n plus 1. And now what we can do is, let's consider applying this formula here on these bounds for every single one. Log 1, log 2, log n. Bit of a annoying, complicated scheme, but it gets us somewhere. And so this will get us, so it's between, I'm just going to call this like, I don't know, s, because I want to. So s is between, so you know, in like derivative of 0 of 1 log t dt, plus, you know, integral from 1 to 2, plus dot dot dot, plus, and then the last integral will be from n minus 1 to n. So that's going to be n minus 1 to n of log t dt. And then similar situation here, where it's just the bounds are shifted up by 1. So your lowest bound is 1 to 2 of log t dt. And then dot dot dot, n to n plus 1 is going to be the log t of dt. So bada bing, bada boom. These bounds are all, you know, just adjacent intervals. So now we have ourselves the integral from 0 to n of log base t of dt is less than s, which is less than 1 to n plus 1 log t dt. And then from here we can just we can use the antiderivative of log. You could do like differentiation by parts. I'm just gonna like, for the sake of completion, I'm gonna do it out. So real quick, let me just check how far on we are on the time. All right, we're 7 minutes in. Okay, cool. And everything's still. Sorry, I'm being so paranoid. Okay, is everything in frame? Yeah, because I just gotta move back like just a tiny bit. Oh, perfection. Okay. So yeah. Okay, what we're going to do is we're going to take the antiderivative. So real quick, just real speed run of log base t of dt. Log base t of dt. We're going to take this as our u, this as our dv. So that means our v is t and our u prime is 1 over t. So that gives us, so this gives us t log t minus the integral of t times 1 over t, so 1 dt. So that's t log t minus t. Bada bing. Record time. We love that. So yeah, t log t minus t is the antiderivative of log t. So that would give us, so if you evaluate this at 0, you get t log t. So log of 0 is negative infinity. And then 0 times negative infinity is 0. Then 0 minus 0 is 0. So bottom bound of bound is 0. So the top bound would be n log n minus n is less than, well, we're going to say for what it is, log of n factorial, right? Because that's all that is, yeah. We started with log n factorial. And that is less than, so this is n plus 1 times log of n plus 1. And it's going to be minus n plus 1. And then this is all going to be minus 1 log 1 minus 1. So 1 log 1 is just 0. And then so 1 log 1 minus 1. This guy is all 0. Minus 1 becomes plus 1. So this is just, I'm just going to write it again. N plus 1 log n plus 1 all minus n. And that's in between, you know. And, okay. Beautiful stuff. So now what we go from here is, now that we have this bound, let's do something completely ridiculous. So I'm going to like set the idea here. I'm going to set a difference variable. Or actually I'm going to call it, not a difference variable. Let me just cutely cross this out. Log variable. Like what the hell is a log variable? I don't know either. I didn't know until a few hours ago. So we're going to call this dn actually. So dn, I'm going to set it up very dramatically with big letters. So I'm going to move the camera. Camera change. Oh yeah, that's the stuff. Then maybe zoom in like a tiny bit. Hell yeah, okay. So yeah, now that we're here, I'm gonna set dn we're going to define dn actually to be, I have to make sure I get this right, log of n factorial minus n plus half, log n plus n. So already you can see a lot of the semblance of the original formula. Like, so this n, when we exponentiate, this will become an e to the n. So e to the negative n is kind of there. N plus 1/2 log n, take this to an exponent, you get n to the n plus 1/2. And the root 2 pi will come later, don't you worry. So yeah, this is kind of the idea. So let's just, for no reason, let's do dn minus dn plus 1. The idea is we want to find, so the general idea, what is like the limit as n goes to infinity of dn. So like, well, what eventually happened to the sequence? Like, does it even exist? Can we even say that? So these are the questions that are looming on our minds. So yeah, these will be answered. So let's take dn minus dn plus 1. You know, kind of consider like, you know, series. When you're doing arithmetic series, you know, it's always constant, so you know it's going to diverge. So things like that. So yeah, let's just do some subtraction. So we get, so to spare you of the forum, so log n factorial minus, and this is kind of necessary, n plus 1/2 log of n plus n, and then you subtract. Yeah, it's like this. It's very similar. Like, it's just like algebra. So sorry about this. Minus n plus 3/2 log. Wait, you have to subtract the whole thing. Minus log of n plus 1 plus n plus 1, something like that. Should you leave it? Yeah, should leave it minus 1. I have to make sure. So yeah, now we just do a bunch of dumb algebra. So we get, so log of n factorial minus log of n plus 1 factorial, divide them. So you get log of 1 over n plus 1 from this term and this term. And then this term and this term will give us, so yeah, we get, I'm going to break up this n plus 3/2 into an n plus 1/2 and 1. So you get n plus 1/2 log n plus 1 minus n plus 1/2 log of n. And then we have to add on another log of n plus 1 plus log of n plus 1. And then n minus n plus 1 is just minus 1. So clearly we see what's going on here. So log of n plus 1, and this is just minus log of n plus 1, because you know, n plus 1 to the negative 1, so you pull out the negative 1. So this guy and this guy cancel. So now you're left with, so this common factor here, that's why I did that. So you get n plus 1/2 times log of n plus 1 over n. N plus 1 over n minus 1. Okay. So as you can see here, you have a lot of things happening. Most notably, this number is positive, because it should be. So we're going to do some stuff here. Trick number 2. Well, I call it, they say trick, I call it deceiving. Because I really feel deceived when coming to this part of the proof. It's just it gets very weird. That's why I even have this. Otherwise, the proof is worth remembering. I will go in later to the philosophy of why this works. Or at least my attempts of it, because it is pretty unintelligible. So this guy here, n plus 1 over n, pretty innocent, right? Some noticing things here. N plus 1 over n, that's greater than 1. So log of 1 is greater than 0. And n plus 1/2 should be greater than, like, you know, as it goes to infinity, like, it should be, like, increasing. That's the idea here. And we will show this. We will say, instead of n plus 1 over n, because that's boring, who needs that? We can call it, yeah, this shit. 1 plus 1 over 2n plus 1 over 1 minus 1 over 2n plus 1. Crazy, right? Well, it works. It just simplifies to 2n plus 2 over 2n plus 1 by 2n by 2n plus 1. So it's just 2n plus 2 by 2n, so n plus 1 by n. A weird way to write it, but you can see that this equals to this. I know, legendary observation. And let's call this t. So now we have it in the form like 1 plus t by 1 minus t. And it turns out, so random fact, I guess those fresh out of a calculus class and those not fresh out of a calculus class will not recognize that 1/2 log of, Jesus Christ, 1 plus t by 1 minus t. That is t plus 1/3 t cubed plus 1/5 t to the 5th, and so on. You get the idea. Also, random question: who learned this? I swear to God, I don't remember this from calculus. It seems familiar, but not really that familiar. But the idea is, we put this t into this t, and stuff pops out. So let's do that real quick. So if we did that, we would get, yeah, let's just so this is, just to be clear, this is this difference. So I'm gonna take this and then do this log stuff. So half log, that's why I half log. So what I'm gonna notice here is that I'm gonna take, so half of log of, I'm gonna write it like this, in our little cube form. 1 minus 1 over 2n plus 1. So this is really just equal to 1 by 2n plus 1 plus 1/3 1 by 2n plus 1 cubed plus 1/5 1 by 2n plus 1 to the 5th plus dot dot dot. You only need a couple terms to get the idea here, but so that's this term of this distribution. The other term is n times this thing. So this is really just 2n times 1/2. So that makes n, right? Log of this stuff from above. So really that just gives us, so this is 1 times this, and this is 2n times the same sum. So really, if you sum both of these, then you get 2n plus 1, I know, pretty, right? Times 1 by 2n plus 1, times 1/3 1 by 2n plus 1 cubed plus 1/5 1 by 2n plus 1 to the 5th plus dot dot dot, and so yada yada yada. So now some nice things happen. This becomes a 1, so everything just turns up 1 exponent. So we get 1 plus 1/3 times 1 by 2n plus 1 squared. So yeah, it all seems too good to be true, which I think holds true for a lot of this proof. This is the really only unexplainable part. This kind of just stems from experimentation, I guess. If you wanted to make some dn like this, even that, it's kind of incredible. It's like seeing an eclipse or something like that. So I don't know. It's very strange. So 1 by 2n plus 1 to the 4th plus dot dot dot. And notice that at the very end we have a -1 very conveniently. So at this series we have the end -1. So -1, 1 cancels. So we're just left with this beautiful series where it's 1 over some odd number, 1 over 2n plus 1 to the odd number -1. And then just for every single odd number greater than 1. I fear I may lose my breath. I don't have any water. So yeah, now we have something interesting. So after all of this, we get, yeah. So we can bound this by the 1/3 here. That's the main thing that we want to notice. So we want to bound this by a geometric series. We want things to be nice. So I actually want to point out that by making this bound, so yeah, right now, 2n minus dn plus 1 is this series. It is exactly this. And so now what we're going to do is, we're going to set, so dn, since dn is so dn is this series right here. Yeah, I'm gonna write it out again. Because it really is nice. It really is nice. And I think it's worth remembering, even if we're gonna dismantle it later. Well, dismantle it right now. Well, let's start with that. So now it's this. And this is strictly less than 1/3. So I'm gonna put 1/3 in front of everything. So 1/3 plus, so yeah, 1/3 of, so 1/3 goes in front of everything. So now it's geometric. Yeah, there we go. So to the 4th. So these are all the even exponents. And so, really, I can also write this equals some small number p plus 1 over like 2n plus 1, p plus, 1/3. Because that's really what the definition of less than is, right? It seems a bit overkill, but I think like when I was reading through the proof, I needed to make this clear for you also, because I found it to be a good clarifying detail. So now, let's not beat around the bush, let's just do this geometric series. So this is a over 1 minus r, good old days. So 1 over 2n plus 1 whole squared, divided by 1 minus 1 by 2n plus 1 whole squared. This is just 1 over, I'm only doing the shit in the parentheses. 1/3 is 1/3 of, 1 over 2n plus 1 whole squared minus 1. Yeah. All right. Let me just check on this real quick. We are still rolling. Beautiful, beautiful stuff. Okay. So yeah. Try not to let this run on too long. Okay, beautiful, beautiful stuff. So now that we've got here, it's just stuff, plus p. Let's not forget the p. And I want to point out the order of p here. So the order of p, it's on the magnitude of 1/15 plus, 1/3 minus 1/5, whatever the hell that is. That number times, it starts with the power of 4. And then kind of just goes on. So it's like something to the power of this factor to the power of 4 plus the same thing to the power of 6, and less and less and less. So actually, what is 1/3 minus 1/5? Ah, 2/15. Okay. So we have 2/15 times 2 to the n plus 1 to the 4th. So this is actually bounded above by, code up. It's on the order of so to the 4th, and then, so when we did with the square, we got something on the order of square. So if we do on something on order of 4, we'll get something around n to the negative 4. And it's something to keep in mind. So now that we have that, what do we do with it? All right. Yeah. Okay. So we get we get here. And there are just some little constructions that I forgot. I actually had written this down. So we just write this as difference of squares. So this is all a bit arbitrary, just messing with numbers as one does. So we factor out the 2's, we get 1/12 times. We get 1 over n plus 1 n, and as we know, you got to break that up. So you get 1/12 times 1 by n minus 1 by n plus 1. Beautiful stuff. Okay. Now that we have that, let's move on. Yeah, seems like a good time to move on. So yeah, now that we have this thing is less than this very pretty bound, really. I'm gonna box it. We should be happy about that. So now that we have that, I want you to notice one thing. So now that we have our dn, I'm gonna put it in a little corner. I'm gonna say, so dn is decreasing because, so while this is positive, it's also less than this bound. And at what point do we prove it's positive? Well, we know that it's equal to this, and this number is in fact positive. So yeah, because it's all equal powers of it's all squares, and squares are all positive. Last time I checked, and it's all odd numbers in the denominator, so it's all going to be positive. So that means 0 is less than dn, which is less than this. So if dn minus dn plus 1 is positive, that means it's decreasing every time. Like if you just think about it, like you have some sequence like 1, 2, 3, 5. 3 minus 5 is negative 2. But like if you had 5, 3, 2, 1, 3 minus 2 is 1. So it's decreasing. So dn is decreasing. Shit, I didn't move the camera. Please don't fall, camera. You're all I have, I think. Hell yeah. Okay. Yes. Okay. So dn is decreasing. What about the sequence dn minus 1 over 12n? If you consider this, so if I consider dn minus 1 over the 12n, so we know the gap is less than this. So then the gap is less than that. So that means, so dn, so if you consider dn minus 1 over 12n, minus dn plus 1 minus 1 over 12n plus 1. So this is very deliberate, right? Because it's literally just we're doing the bound. So this is less than, it's less than the bound. So really we just have like, this equals to rp plus 1 over 12, 1 over n minus 1 over n plus 1, and then we subtract, so yeah, minus 1 over 12n plus 1 over 12n plus 1. So as you can see, despite the bad handwriting, everything does cancel. Or like, yeah, something like minus p or something. Let's not worry about p actually. But it does turn out to be just like, if you do it out, it's just less than 0. So all these cancel and then you get like it's less than 0. We'll keep the strict inequality. Don't worry about p. So this is less than this, which equals 0. The kinks are kinks. Yeah. So now dn minus 12n, since the difference is less than, since the difference is less than 0. Yeah. Because like if you're going from 3 to 5, 3 minus 5 is minus 2. That means this guy is increasing. So look at what we have here. So dn is decreasing, and dn, based on some factor of n, is increasing. So this will eventually go to 0. So since dn is decreasing and dn is increasing in some way, this means dn has to converge. dn converges at some constant c. So I'm going to erase the stuff at the top because you already know the problem statement by now. Or at least I hope you do. I'm just kidding. Yeah. We're going to keep dn. It's too legendary. Yeah, maybe we'll keep the theorem statement up. And we'll get rid of all of these. And, yeah. Okay, I'm back. The camera decided to magically stop being a camera for a second. So that was beautiful, and I lost like a minute's worth of progress, so it's fine. So now that we have all of this, now that we know that dn converges for some c, let's exponentiate. So we're just going to go back to the n factorial. So we're going to go back to this. Because we were working in log world for a long time. Let's come back to the real world. So let's consider, so since this equality holds, lim n dn as n goes to infinity some c, if we exponentiate everything, we get, limit as n goes to infinity of e to the dn, is e to the c, right? If c is what dn comes out to. So this is pretty obvious stuff. And now what we do is, the nice stuff is we exponentiate dn. So dn is written up here. So we have, so e to the log n factorial is just n factorial. And then, minus becomes divide. So you get, so n plus 1/2 log n. If you take that exponentiate, the log n becomes the base. So n is the base, and then n plus 1/2 the exponent. So n plus 1/2. And then, so I'm just going to write this as e to the negative n in the denominator. We're dividing by e to the negative n. It is a plus n. So this will cancel and be a plus n. I left my notes around here. Necessary to speed up the process. Apologies. So now we're going to do something completely different. So this is going to be equal to e to the c, by the way. This is going to be e to the c, yeah. So as you can see, everything's coming together. N factorial is equal to e to the c times n to the n plus 1/2 times e to the negative n. We literally have the formula. If you move this over here, we have the formula. Now all there's left to prove is, so yeah, I'm just actually going to write this out because it's so glorious, right? E to the c times n plus 1/2 times e to the negative n. We're almost at the form. We just have to prove that this guy is equal to square root of 2 pi. So now pi has dipped his pi into this business, and we have to do something completely different. So introducing the Wallis product. I was trying to build suspense. Hopefully you didn't read the Wallis product that I already erased up here. So Wallis product. If you don't know Wallis product, it's very famous, but it's really not that useful, so it's not a big deal. So 2 times 2 over 1 times 3. Actually, this is the limit as n goes to infinity. N will come later. So 2 times 2 times 1 by 3, 4 times 4 by 3 times 5. Yeah, you get the idea. Times such as that. So 2n whole squared over 2n minus 1, 2n plus 1. And as you keep taking products like this, so the idea is you take something slightly smaller than 1, slightly greater than 1, slightly smaller than 1, slightly greater than 1, you have 2 1, 2 thirds, 4 thirds, 4 fifths, 6 5, 6 sevenths. And eventually you get to, what is it? Yeah, pi over 2. Yeah. So why would I believe this? And you have a good point. Why would you believe this? So let's provide a proof. So actually we're going to use trig. The idea with being trig, when you do like integration by parts, sometimes you leave fractions as residues, and you get lower powers. That's the idea here. So if we do 0 to pi over 2 of a cosine to the t dt, well, cosine of n, sorry, dt. So we're taking cosine t to the nth power, and we're integrating it from 0 to pi over 2. And these bounds are actually very specific, because it's really nice. So yeah, the idea here is we break this up into 0 pi over 2, cosine to the n minus 1 t times cosine t dt. So this is going to be your b prime, this is going to be your u. I'll save you the pain and do it myself. We have u is cosine to the n minus 1 t, v prime is cosine t dt. And then u prime is, so that's going to be n minus 1 cosine to the n minus 2 t. And then cosine, derivative of cosine is minus sine of t. And a v itself is just going to be sine, because antiderivative of cosine is sine, obviously. So now we do our little, this thing, you know. So now we get uv minus the derivative, integral of v du. So that gives us, hold up. So what's uv in this case? Sine. Okay. So cosine n minus 1 of t times sine of t from 0 to pi over 2. I want to make sure you're still rolling. I got paranoid from the first time. Oh shit, we are still rolling. 5 minutes in. Okay, good. And then minus, well, the minus becomes plus. So I'm just going to write plus, because this minus becomes a plus when you do minus. So you get sine squared, by the way. Yeah, so I'm just going to write it. So from 0 to pi over 2, same bounds, of n minus 1 cosine of n minus 2 to the t times like sine squared of t. So this becomes 0 actually, because cosine of pi over 2 is 0 last time I checked, and sine of 0 is 0. So both of these terms are going to be 0. So yeah, this is all just going to be 0. So don't even worry about it. 0. And so now we have one integral, and we start with a different integral with a smaller power, but also not really because we have a sine squared. So we can get rid of the sine squared by just letting it be 1 minus cosine squared. So then we just let this be, 0 to pi over 2. Josh would be happy with all these integrations, maybe. I don't know, he has high standards. N minus 1 cosine of n minus 2 to the t. 1 minus cosine squared t dt. So as you can notice, we have this n minus 2 and squared makes back our original power. So this will be 0 to pi over 2 of, so I'm gonna bring out the n minus 1. And then cosine of n minus 2 of t dt. I'm going to distribute over this 1 minus cosine squared minus n minus 1 times the original integral. So so that means if this is the n minus 1 times the original integral. So if you just do some algebra, you get our original integral I. I'm just going to call this I. This guy is now I. So I is just equal to n. Actually, I'm not going to call it I. We should write it out. 0 to pi over 2 cosine to the n of t dt. Just to be clear. So this is just equal to n over n minus 1. N minus 1 from here, and n, so plus 1. N minus 1 plus 1 is n. So this gives of the smaller power. So 0 to the pi over 2, sorry, I'm comparing, cosine to the n minus 2 to the t dt. So I want to make sure I have that right. I have this written down. So yeah, and this is for n greater than or equal to 2. What from here can we erase? The entire thing? Yeah, the entire thing. We can get rid of the entire thing. 1 sec here. Nine minutes 24. I'm gonna stop it. All right. I suppose we're back. The idea being, the idea being we're just gonna keep doing stuff with this, and then prove the Wallis, and then using Wallis, we'll just be able to, the proof will pop out. And proof will just pop out itself at us. So now what we're gonna do is, I kept the definition there. I mean the bound that we got. The definition bound. So now that we have that, So yeah, the thing is like repeatedly using this will pop out more and more fractions. Because if you have a, so if we have an even case, right, we can just keep doing this until we get cosine to the 0. So the idea is, so even case. So I'm going to do, get away that. Even case, 0 to the pi by 2 of cosine to the 2n of t dt. So this is 2n minus 1 over 2n times the same integral except with cosine of 2 times n minus 1, like in parentheses, because the power goes down by 2. So you just keep doing this over and over, and eventually you get, so you get the product, yikes, you get like pi over 2, or you get, so 2n minus 1 by 2n times 2n minus 3 over 2n minus 2 times dot 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 1/2 the integral from 0 to pi over 2 of cosine to the 0. Imagine that. So that would just give you, just gives you pi over 2 times the product from k equals 1 to the n of 2k minus 1 over 2k. So n greater than or equal to 0. I feel like this Wallis product proof is completely unnecessary, but it's so fun. I got lost in it for a sec. So this is 0 to pi over 2 of cosine to the 2n plus 1 t dt. So this will take you down to 1 actually. So notice that like every time like the biggest fraction is just like the number minus 1 over the number itself. So the same thing here. So it's 2n over 2n plus 1. Should be. Hold up. So like times, dot 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 times 4/5 times 2/3. It's really just, and then like the integral at the bottom like doesn't even really matter because it's just that's pi over 2, and then this one just like with trig and stuff, so it doesn't like since there is a cosine, like the numbers just become normal. Like if you do cosine of pi over 2, that's 0. So it just doesn't really matter. So now you have k is from 1 to n of 2k over 2k plus 1. Look at that. Look how clean that is. Isn't that beautiful? So now what we do is, so notice that like the more terms so the greater this exponent you make, you keep multiplying by like whatever your last result was, like times 2 to you could multiply by 2 to the pi, so that makes it significantly worse. And then you multiply by like a small factor, so that's less than 1. So in any case, you have as you're decreasing the exponents, the values increase. So you get 0 is less than, strictly less than, 0 to pi over 2 of cosine to the 2n plus 2 t dt. I think you can see where I'm going with this. I'm going to just change the exponents, that's all. So cosine 2n plus 1 t dt less than 0 of pi over 2 cosine of 2n to the t. So that's that. So that's a kind of a actually that's equal to, I guess. Then just n is greater, n is non-negative, no doubt. So now we can see that these two, so these are off by a factor of 2, power of 2, or a factor of 2n over 2n plus 1. So I'm going to say 2n plus 1 over 2n plus 2, is less than or equal to this factor, 0 pi over 2 cosine of 2n plus 1 of t dt over 0 to pi over 2. So really these are just like things that or actually my numbers were wrong because it's like plus 1. But 2n t dt. So the fractions will out themselves. This is less than or equal to 1, by the way, because it's smaller. That's one of the key parts of this. This 1 will come in handy. So now, if we just divide using the products themselves, the top becomes 2/3 times 4/5 times dot 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 times 2n by 2n plus 1. Bottom becomes pi by 2 times 1/2 times 3/4 times 2n minus 1 by 2n. So notice that all of these will come up to the top. So these will meet their match. So this will give exactly, so this is 2 over pi, by the way, times 2 times 2 by 1 times 3 times 4 times 4 by 3 times 5. Hey, look at that, it's the Wallis product. 2n squared by 2n minus 1, 2n plus 1. So yeah, that's that. I don't know what to do now. Well, actually I do know what to do now. I don't know why I said that. So yeah, now the Wallis product. So this is so as n goes to infinity, this will become 1. So now this is 1 and this is 1 by squeeze theorem. This is 1. Wow, I haven't seen the name squeeze theorem in a while. So this is just the Wallis product. So Wallis product, so 2 over pi times Wallis product is 1. So Wallis product is pi over 2. Look at that. Whoop-de-doo. Delight. Yes. QED. Bonanza. Yay. So yeah, now that we've proven the Wallis product, we can forget that we ever learned it in the first place. Let me just see how our camera's doing. He's going strong. Hang in there, buddy. Oh my god. Whew, this is tiring. But I love it. That's why I'm doing it. I'm so hungry, by the way. It's crazy. So yeah, there we go. It's okay. I started myself my own entertainment. What is you, anyways? All right. Let's see. Just kidding on the Wallis part, by the way. Food here is not good. I'll say that much. But yeah, now that we have the Wallis product under our belt, now that we've proven it and we're happy with ourselves, yeah. So now let's move on. There's one last part. So yeah. So now that we have like, let's just write out the Wallis product again. 2 times 2 by 1 times 3 times 4 times 4 by 2 times 5 times 2n squared by 2n minus 1, 2n plus 1, equals pi over 2. And this is limit as n goes to infinity. So if we were to, well, yeah, let's choose n large, okay? Because we're trying to, do this approximation for a large n. And that means that, so yeah, we have like 2 times 4 times 2n, all squared, over 1 times 3 times 5, like 1 times 3 squared times 5 squared, or 1 squared times 2n minus 1 squared, times just 2n plus 1 once, is approximately pi over 2. Now let's square root everything. So this would give us 2 times 4 times 2n over 1 times 3 times 5 times times 2n minus 1 times square root of 2n plus 1. Well, actually, let's just not choose n large. Let's just choose n infinity, basically. So this is going to be equal. And so this is going to be equal to pi over 2. So I'm just going to do an approximation here. 1 by square root of 2n plus 1 is approximately equal to 1 by square root of 2n. So I'm just going to change this to 2n basically. So if we pull out all the factors of 2, this is just a factorial but doubled at each term. So you have 2 to the n times n factorial over. Note that if you put a little even number in between here, you could get a new factorial. 2n factorial, in fact. So if I put like a little 2 here, if I multiply by 2, multiply by 4, multiply by 6, multiply by 2n, and then multiply by 2, multiply by 4, multiply by 6, multiply by 2n. Awesome, now we have another 2 times 4 times 6 up to 2n. So this is 2 to the n times n factorial over, now we have a full 2n factorial. Times square root of 2n. Well, that's old news. Doesn't matter. This is approximately square root of, before I got the square root here. Square root of pi over 2. And, by the way, this is where we use our definition of our n factorial. So since we know this fact, n factorial is equal to this guy. Well, it's about this guy. Like, since we know in the limit it's equal, it's about. So every time we see an n factorial, we're going to replace it with this monstrosity expression on the left here. I'm just going to like move the camera real quick. Or actually, I think you can see it. But yeah, it's this part that I've like put in braces, and like n factorial is e to the c times n plus 1/2 times e to the negative n. We're just going to replace it with that every single fucking time. Then we'll be done. So yeah, I'm just going to like write this out by hand because the algebra is really boring. So this will be, yeah, every time we replace, n factorial is about e to the c n times, or n to the n plus 1/2 times e to the negative n. So yeah, that's what we're replacing it with, by the way. So then we get 2 to the 2n. This is for the sake of rigor, by the way. 2n plus 1, e to the negative 2n, e to the 2c, by 2n to the 2n plus 1/2, e to the minus 2n, e to the c, times 1 by the square root of 2n, which is around pi by 2. So yeah, this guy cancels, e to 2c to the c gone. Other stuff happens, then you get, yeah, this stuff simplifies too, by the way. E to the c is around the square root of 2 pi, just trust me. It's a very simple algebra. Yeah. And since they are constants, you could just say it's equal. And so now we have e to the c is square root of 2 pi. So now you have n factorial is about e to the c, n to the n plus 1/2, e to the negative n. So now that's approximately square root of 2 pi, n times n plus 1/2, e to the negative n. QED. Yay, we're done. I was going to make some closing remarks. I'm really hungry and really tired. Just thanks for like being my friend, I guess. I mean, I don't know why I'm saying that, but like it's just nice that, that's why part of why I decided to do this. Part of it for myself, part of it for you. So yeah, thank you.